I would like to share this. Okay, so I would like you to tell me how you use physics, for example, for safety, when it comes to traffic, electricity, heat, and stuff like that, yeah? So that's what I would like you to tell me. Then I would like you to round your student number to 7 significant figures. So regarding rockets, it should be okay. I don't really ask you about that. Projectile, I don't really ask you about that. Moment of inertia. Now, when it comes to these things like moment of inertia, Coriolis force, etc., I ask you about this in question number 31. Okay, question number 31 asks about everything. Yeah. So if you feel that you want to share something about Kepler's laws or quantum physics or general relativity or whatever, you answer those in question number 31. Yeah. This section of standing waves is even more important because I ask you all these questions. Any standing wave must have an integer number of half waves. Yeah. In a standing wave, the places with zero amplitude are called nodes. Yeah. A standing wave with greater frequency corresponds with greater energy. Okay, let me. Yeah, so we are doing Google Meet today. Okay. Okay. So please answer these questions about standing waves. Yeah, it's either from the video of Professor Dave or from this text. I took it from Professor Dave from YouTube, so you can use whatever you want. Yeah. I don't remember asking you about the songs, but you can answer about the songs in question 31 about quantization as well, and this general stuff about classical physics, frequency, friction, elasticity, plasticity, fracture, thermodynamics, which all have the physical foundation of electromagnetism. Yeah. Oh, as you probably know now, a very big iceberg is in the water now, in the ocean, if you follow the news. So what happens if all the icebergs which are which are floating, what if they melt? If they melt, the level of water will not change, right? But because it's moved from Antarctic to the water level has already increased already. But if they all melt, in case if they all are floating, then the water level will not change. If all the floating iceberg melt, the water level will not change. We use our knowledge in thermodynamics and in fluid dynamics to answer this question, okay? The resistance force in the fluid, for example, to soccer ball or to tennis ball or to bullet or to cannonball or whatever, this is the formula, and I ask you to write your student number instead of this and give the correct number of significant figures for the resistance force, okay? Okay. Now, Euler's and Navier-Stokes equations, they are all for question number 31. If you can understand that, if you can write about it, just write a few words about those topics which you understand, yeah? So now I ask you about this stretching cat. So usually if it is too hot, cat stretches to cool down. And that's how we increase the thermal exchange. We stretch to increase thermal exchange with the environment. Yeah. The heat exchange happens through conduction, convection, and radiation. So when CAD stretches, it increases conduction and maybe a little bit of convection with fluid, which is the air and his body. So conduction is in the solids, convection is in fluids, and radiation is through vacuum. Yeah. So therefore, you must explain why CAD stretches to cool down, using this idea that the more is the area, the more is the heat exchange with the environment. Okay. Let's see who else wants to join us. No. Okay. So let me see if I can go to Zoom here. I can do Zoom and Google Meet at the same time. Not? I'm trying. It says invalid meeting ID. Okay, let's continue in Google Meet. I don't know why I cannot access. Okay, let me start the session. Hope I can start the session. Okay, so therefore, please explain the heat exchange. If CAD stretches, the heat exchange increases. Yeah, and this happens through conduction, convection, and radiation. Okay. If you understand conduction, convection, and radiation, please write about it in question number 31. Just like if you understand thermodynamics laws, you also please write about it in question 31 in your task number 2. Yeah, task number 2, question 31. So the laws of thermodynamics: first law, second law, which is the most important law, it talks about increasing entropy and increasing chaos in the world. So it has very deep philosophical meaning. So we must try to, fight in order to keep diversity in our world, so that we can survive, we can live good lives. Yeah, we need to fight for that. Yeah, otherwise it will be messy. Otherwise, things will get messy. So that's basically what second law of thermodynamics says. It mostly talks about thermodynamics and temperature difference, but it's not only about temperature, it's about order and mass in general. Yeah. Also third law of thermodynamics and first and zeroth law of thermodynamics. So you must know what entropy is. It's the measure of chaos. Yeah. Enthalpy also another important notion. You need to know what is work of gas. Basically, it's product of pressure and volume. That's work of gas. Okay. Heat energy, another notion. Let me on the AC very quickly. Just a second here. Hopefully that's better. So heat energy, you need to know the definition. And if you know it, you write it in question number 31. Then you check out Google, textbooks, websites, YouTube. Yeah. And also internal energy. We know what internal energy is. Yeah. Now, we must know what isothermal process, adiabatic process, isochoric process, and isothermal process are. And so basically, isothermal means temperature is the same, isobaric means pressure is the same, isochoric means volume is the same, and adiabatic means no thermal exchange. We need them to deal with heat engines. So I ask you to calculate the efficiency of heat engine. So please do calculate. Obviously it will be 0.5 to one significant figure. Yeah, but please do calculate. Yeah, question? Just a moment. Just a moment, let me see. Yeah. Sorry. So, so please calculate the efficiency of the heat engine. It should be 0.5, obviously, one significant figure. Yeah, and also the temperature. Here, also one significant figure is calculated using whatever methods you want, maybe macro in Microsoft Office or whatever. Yeah. And it's done to understand Carnot's cycle, Otto cycle and diesel cycle. Those are combustion engines. So Carnot cycle is external combustion engine, Otto cycle is internal combustion engine, and diesel is internal combustion engine. So diesel is the most efficient. Otto cycle is gasoline engine. Basically, it's kind of in the middle. And the least efficient is Carnot's cycle. It's about steam engines cycle. Yeah. So once again, if you understand any of this, please write your answer in question number 31. We already know that the sun is either blue or green. We have answered that before. And now in optics, lenses, mirrors. So if you understand about those, please also write in question number 31. Light absorption, same thing. Write about it in question number 31. Now, for compound capacitance, we need to calculate, yeah? We need to calculate, and it's only one significant figure, so please calculate the compound capacitance for parallel case and for series case, yeah? So please do that. Do calculate. I give you the units, and I give you one significant figure, so you don't need to find out how many significant figures are there, okay? Only one significant figure, but please do calculate, yeah? Now, the resistance of inductor to direct current is 0. Yeah, it's just a piece of wire. It does have resistance, but to alternating current, sorry. But the resistance of inductor to direct current is 0. Yeah. So if you understand Lorentz force, please write your explanation in question number 31. Same thing about Maxwell's equations. If you understand them, please write in question 31. There are no magnetic charges known in our part of the universe. Of course, there are electric charges. Yeah. So if you understand the modulation, jamming signal, and physics of drones, then please write in question number 31. Yeah. Question number 31 includes all general things, all kind of general explanations like that, okay? Now for atomic physics, here, please calculate the distance, approximate distance between your particles. So please write your student number here, and for your student number, please find the element. If it is not here, for example, I have only 9, 12, 15, 16, 17, 18, 19, 22, 25, 26, 29, 35, and that's it, right? If it is not your T number, which is your student number mod 100, if it is not here, then please do it, copy it from a periodic table. So you need your T number, which is atomic number, and then atomic weight in kilograms. It's weight, but in kilograms, yeah. And density in kilograms per meter cube, and then go to 1. So it will calculate the approximate distance between your atoms of your element, yeah. with this atomic weight and with this density. Yeah, so please do that. Please do that for your student number. If your number is here, then you don't need to do anything. But if your number is not here, please do it. Yeah. Okay, and it's only one significant figure. Okay. Let me see. Okay. So please do it for your student number. For copper, I mean it's okay. I'm asking you for all of them, not only for copper. Yeah. So you calculate approximate distances between the particles, and here you calculate energy and momentum of photon. Yeah. So please write your student number instead of this, and you don't need to calculate this time. Just give the correct number of significant figures. Just your student number in here instead of this, your student number instead of this, and correct number of significant figures. Yeah. And also for the wavelength, your student number here instead of this, and also the number of significant figures. No need to calculate here. Yeah. Same thing for the wavelength of electron, your student number instead of this, and correct number of significant figures depending on your student number. You need to calculate. Okay. Okay. So once again, the student number is here, and the matter wave of the desk, or whatever it is, and please don't calculate, but give the correct number of significant figures. Yeah. Let's see who else tries to enter. Okay, I admit. Okay. So just write your student number and correct number of significant figures. And in this case, no need to calculate. For hydrogen, using Bohr's model, once again, please write your student number instead of this and give the correct number of significant figures. And that's it, no need to calculate. Yeah. Obviously, massless particles are better for quantum computing, and this question perform a correlation and a regression analysis. Basically, it shows that the heavier the particle, the shorter it is lifetime on average. Yeah, on average, statistically. So just like people, usually heavier people, they cannot live long usually. Yeah, same thing for particles. So kind of a parallel between particles and people. So we kind of sort of analyze particles. And now, what particles mediate electromagnetic interaction? Well, photons. So the answer is D. So photons are bosons of electromagnetic field. What particles mediate strong interaction? Gluons. Gluons are bosons for strong nuclear force. Okay, let me see. Okay, I hope I admitted everybody. Okay. Okay. What's next? Okay, this question is the same because we have done photons already, so I don't ask you this. So we don't know structure of electron, but we know structure of neutron and proton. As you can see, neutron has the structure of down-down-up quarks, and then proton has the structure of up-up-down quarks. Okay, so that's the structure of proton and neutron. Okay, so annihilation energy, please once again write your student number instead of this and give the correct number of significant figures. If it is like 4, then 4, if 3, then 3, if 2, then 2, if 1, then 1, whatever your K number is, yeah? Okay. So no need to calculate, just your student number in here and correct number of significant figures in this case, as usual. So your student number here for decay and the correct number of significant figures, whatever it is, 1 or 2 or whatever. Yeah. If you calculate here, the remaining mass is not 0 because it is never 0. Okay, let me check what happens here. Okay. Because exponent will never reach 0, no matter how big the number is, it will never be 0, no matter how small it is, it will never be 0, because that's the property of the exponent, yeah? So don't write 0 as the answer. Better write your student number here and correct number of significant figures, and that's it. And don't calculate in this case. Okay. How many times electromagnetic force is weaker than strong nuclear force? 137 times approximately. Yeah. So once again, this is for question 31, drop model of nucleus. Yeah, alpha, beta, and gamma radiation. So the ionizing effect and penetrating effect, depending on the type of radiation, right? If you know what depleted uranium is, also write in question number 31. Yeah. Nuclear reactions, please describe them in question 31. Nuclear fission and nuclear fusion, describe them in question number 31 if you can. Quantum tunneling, same thing. Yeah, how can we survive nuclear war? The question also in question 31. Quantum computing, question 31. General relativity, question 31. Prize in physics of this year, 2023. Question 31, please. So whatever you can in terms of the words, like about theories, about laws, concepts, anything like that, all in question 31. Everything else, then usually you need to write your student number. Sometimes you need to calculate. Sometimes you need to give the correct number of significant figures. Those are separate questions. Yeah. Okay, now hydraulics. Here I ask you to calculate. And if you know what is hydraulics and what is pneumatics, then answer this in question number 31. But this question, when you press a pedal, I ask you to calculate. So your force will be 100 times bigger. So please type your student number here and give the force, the number. What is, how many newtons? How many newtons? In my case, it will be 600 newtons. In your case, maybe something else. Yeah. Because my L is 6, but your L may be different. So the increase in force is 100 times. Yeah, so if your L number is, for example, 7, then the resulting force will be 700 newtons. If you press with force of 7 newtons, then it will amplify 100 times. So it will be 700 newtons. Yeah. So are these statements true? So similarity of mechanics, fluid, and thermodynamics. Mechanical system moves from high potential energy to low potential energy. Fluid flows from high pressure to low pressure. Heat flows from hot to cold, from high temperature to low temperature. Well, for classical physics, it's almost always true, but the more you go into modern physics and quantum physics, sometimes it's not true. Everything is possible in quantum physics with certain probability. Yeah. Let me see. Okay. Let me admit this student. Okay. So, yeah, so these are philosophical questions. If you can talk about space debris, please do in question 31. The planetary model of atom or Bohr's model, again, question 31. About bosons and fermions in question 31. Number in question 31. Schrödinger's cat, question 31. Schrödinger's equation, question 31, Dirac equation, question 31, uncertainty principle, question 31, Big Bang, question 31, if you understand, only if you understand. String theory, question 31, aliens or extraterrestrial life, question 31. Okay, so questions or comments or anything about the task 2. Okay, so we have gone through lecture number 5. I would like to see who is present. And then after that, we'll go to lecture number 6 probably, yeah? Let's see who is present. Okay, Bayu Arif Setiawan, Muhammad
Present.
Muhammad Diyar Ramadhan, Nabhan Muhammad Raihan, Rul Nabila,
Yes, sir.
Rul Ilham, Ahmed Andhika Putra Pratama, Ibn Salam, Adam Apriyansya, Ranga Raditya Putra Pratama, Muhammad Farid Ali Wahyuddin, Muhammad Fauzan Bintan Avdisa, sorry. Renelia Raisha Wulur, Virgi Fabrian Hermawan.
Present, sir.
Okay. Let's see if I can find other students. Okay. Okay. Melissa Claudia Sapitri,
Present, sir.
Christian Jonathan Pascual,
Present, sir.
Siti Raihana,
Present, sir.
Arief Aprilianto, Arief Aprilianto. Okay, Grandi Damar Negara,
Present, sir.
Ali Sirajuddin, Brian, Jonathan Utapea, Muhammad Haikal Bagus Putra, Muhammad Naufal,
Present, sir.
Sabrina Fitria
Present, sir.
Ramadhani Napitupulu. Okay.
Present, sir.
Thank you. Hopefully I have marked everybody who is present. Okay. So, any questions, any comments, please? So I hope that you can submit your task 2 by end of 12th of December. I hope it will be enough time for you to answer everything, yeah? And we answer that in class, every class, yeah? So, having said that, let me admit this person. And let us do lecture number 6. So let me close lecture number 5. And let me do lecture number 6. Okay. So, lecture number 6. So lecture number 6. So acoustics. We have been dealing with acoustics for a while, so if you understand what it is, just write it in question number 31. And here I ask you to give the ground state configuration for atom T in periodic table, right? For hydrogen, it's 1s1, yeah? For whatever your T number is, you take it from periodic table and write the ground state configuration. You can find it on the internet, you can find it in YouTube, on YouTube, in the textbooks, on the websites, you know, you can find it. And for Planck's constant, about Planck's constant, you can write in question number 31. We've been dealing with Planck's constant for a while now. Yeah. So electron volt is just another unit of energy. So you can convert from joules to electron volts. Yeah. And this one I would like you to calculate. So your student number must be here instead of this fake student number. And it's only one significant figure. So this time I ask you to calculate, because it's only one significant figure, I give you the number of significant figures, yeah? So this time, so you calculate what is the difference in energy. Okay, so please calculate this, writing your student number instead of this fake student number. Okay, that will be the energy released, right? Energy released. Oh no, energy absorbed, right? Energy absorbed by electron to move from N1 is equal to T to N2 is equal to S, where S is your student number and T is your student number mod 100, yeah? So Z is equal to 1 for hydrogen, so just your student number here, and calculate energy. So main nuclear reactions and safety of nuclear technologies in question number 31, excuse me. How many dimensions are there in our universe? Maybe 10 or maybe 26, depending on the theory that you use, sorry. 26 maybe. It should be fine. Even if you say 3 dimensions, you can still accept that. Yeah, so maybe you can answer either here or in question number 31. So I would like you to watch these lectures in physics on YouTube. They are very good, and there are many other lectures which are very good. Please try to watch at least some of them, especially about those topics that we discuss, some classical physics topics like hydraulics, pneumatics, and fluid and thermodynamics, and also modern physics like quantum physics, nuclear physics, particle physics, like annihilation energy, antimatter, and then other topics of modern physics, yeah? Now, standard model, if you understand what it is, write in question number 31, yeah? Dark matter, question 31, dark energy, question 31. So black hole as quantum computer, question number 31. If you can watch this video, it's very long. So please don't watch it if it is too hard for you. But if you can, please watch this video. And if we can connect black hole and quantum computer, that would be great. A wormhole is a tunnel between different parts of the universe. Okay, so that's for question 31. Scattering and spectroscopy are the main ways of analyzing substances and galaxies and everything. So if you understand them, please write about them in question number 31. So physical constants and what my PhD thesis was about. That's what my PhD thesis was about. So if you understand physical constants and variation of physical constants, then write about it in question number 31. Just like Hall effect, if you understand what it is, write in question number 31. Yeah. So if you understand what lepton is, what neutrino is, neutral particle with very small mass, write in question number 31. Okay, Higgs boson, another important boson of standard model. If you understand what it is, write in question number 31. Vacuum, another important definition. So maybe energy of vacuum is very big or even infinity, according to some theories. Maybe we can get energy from vacuum. Another important notion, another important definition. So if you understand, write about it in question number 31. Same thing about parallel universe. And theory of everything, also question 31. Quantum field theory, question number 31. Rydberg's constant, question number 31. Questions from students. I think you asked this one. No, not you. Another student asked. Well, I have already answered it quite correctly, and as you can see, the Google confirms me. Basically, laws are more specific, whereas theories may include several laws. Yeah. So it was before the Big Bang. Maybe nothing, according to most physicists. There was no matter, no time, no space. But maybe there was no Big Bang, or maybe Big Bang was just the clash of parallel universes. So there are so many theories. And the difference between weight and mass, yeah, sometimes they're similar, but sometimes they're different, depending on the situation. For example, Einstein tried to prove that gravitational mass and inertial mass are the same, but sometimes center of mass and center of gravity are different, especially if you have different planets, different stars, and the object which is kind of big and comparable in size to the planet. For example, a railway from Lisbon to Beijing, for example. Yeah. So in that case, center of mass and center of gravity are different. Yeah. I think one of you asked, can quantum computer help with theory of everything? Well, I hope so. I hope it can help to find the theory of everything in physics, and also theory of everything would probably help with quantum computer as well. And how can people be teleported? I don't know. Maybe it will never be possible. At the moment, we have quantum teleportation and less than 200 kilometers. We need at least 200 or 300 kilometers so that we can teleport to the orbit, to the satellites. So that will help telecommunication quite a lot. Okay. Pauli exclusion principle for fermions, if you understand it, please write in question 31. Parity violation, also question 31, please. Teleportation, if you understand quantum teleportation, question 31, please. Quantum entanglement, also question 31. Quantum cryptography, question 31. Polarization, question 31. Quantum chromodynamics, question 31. Bose-Einstein condensate, question 31. Nuclear reactor, question 31. Nuclear weapon, question 31. I don't like that, but so this is the question 31. Finally, we got to it, yeah? So it says, explain main concepts, law theories of the physics, which means the physics that we study mostly after the midterm exam, yeah? So, excuse me. After the midterm exam, those topics like hydraulics, resistance in the fluid, temperatures, efficiency of heat engine, and then quantum physics, and then nuclear physics, and antimatter, annihilation energy, momentum of photon, energy of photon, Bohr's model of atom, that kind of stuff. Yeah. So some of you, some of the questions must be either calculated or adjusted, like with your student number, with the number of significant figures. And if it is about theory, for example, about theory of everything, and if you understand theory of everything, for example, string theory or whatever, you write about it in question 31 in your own words. So all those general things, they all go into question 31, okay? They all go into question 31. A white hole is kind of opposite of black hole. It may or may not exist. People don't really know, but there's a theory of white hole. So question 31, please. Compton effect, also question 31, it's about scattering. Body radiation problem, very important problem solved in 1900 by Max Planck, which basically started quantum physics. If you understand that, please write it in question 31. Yeah? Well, nuclear fusion, that's probably one of the most important topics for people to have enough energy and clean enough energy and cheap enough energy. So if you understand nuclear fusion and controlled nuclear fusion, please write about it in question number 31. Okay, so any questions, any comments, please? Okay. Okay. So, if you don't have questions and if you don't have comments, then why don't we watch some of those videos? Okay, I have set the keyboard. Okay, so let's try to watch video about nuclear reactor, for example. There we go, nuclear reactor. Let me see if I can find. There we go. Nuclear reactor.
Fossil fuels like coal. Nuclear reactor. In this video, we're going to learn about the nuclear reactor. Nuclear reactors are the modern day devices extensively used for power generation, as the traditional fossil fuels like coal are at the breach of extinction. A nuclear reactor is the source of intense heat, which is in turn used for generation of power in nuclear power stations. Its mechanism is similar to that of a furnace in a steam generator. The steam is used to drive the turbines of the electric generator system. A nuclear reactor consists of three crucial components: fuel elements, moderator, and control rods. Fuel elements come usually in the shape of thin rods of about 1 centimeter in diameter and contain fissionable neutrons like uranium-235 or uranium-238. These rods vary in number according to the size of the reactors. In large power reactors, thousands of fuel elements are placed close to each other. This region where these fuel elements are placed is called the reactor core. These fuel elements are normally immersed in water, which acts as a moderator. The objective of a moderator is to slow down the energy neutrons in a nuclear reactor, which are produced during the nuclear fission process by the fuel elements. Thermal neutrons, which are the neutrons with energy of about 0.04 electron volts, are capable of producing fission reaction with uranium-235. During the fission reaction process, new neutrons are given out, which have energies of about 1 MeV. This is 1 mega electron volts. These neutrons typically escape from participating in another fission process, as they are accompanied by enormous energy release. In fact, the probability of these neutrons produce another fission reaction is 500 times less than that compared to a thermal neutron. This is where a moderator is extremely useful. Moderators have the capability to slow down, or in other words, moderate, the speeds of these high-energy neutrons so that they can in turn be used for a chain reaction to trigger multiple fission reactions of other uranium-235 nuclei. Commonly, ordinary or heavy water is used as a moderator in nuclear reactors because of the deuterons present in them, which are capable of slowing down the neutron speed. Water molecules like moderator are useful in slowing down the high-energy neutrons, which leave the fuel element after nuclear fission. These high-energy neutrons collide with water molecules, thereby losing out on some energy with every collision and therefore slowing down substantially. A new fission reaction can now be triggered using this slow neutron by striking it with a fuel element. The third and most prominent part of a nuclear reactor are the control rods. In order to get a steady output of energy from the nuclear reactor, every single fission reaction should trigger another fission reaction and ensure the availability of spare neutrons released to trigger the chain reactions. By controlling the number of spare neutrons available at any given time, the rate of nuclear fission chain reactions can be controlled. This control on the fission reaction can be maintained using control rods. The main function of the control rods is to absorb any excess or spare neutron in the moderator in order to prevent any further fission reactions. Usually, such control rods are made of boron or cadmium. To increase the rate of fission reactions, these rods can be removed from the moderator. A steady output of energy can be maintained by inserting or removing the control rods in the nuclear reactor. Now that we know the components of the nuclear reactor, let's understand the working of the nuclear reactor. It's usually enclosed in a shield made of thick concrete walls. It consists of a reactor core, pump, and heat exchanger. The reactor core and pump are placed in contact with the water, which is usually the heat exchanger in these reactors. Due to the enormous amount of heat released during the fusion reaction, the surrounding water gets heated up and changes to steam, which is in turn used to turn the turbines. So, huge heat energy gets converted into electrical energy. Water is continuously flown in and out of the nuclear reactor using the pumps. So, a nuclear reactor successfully generates nuclear energy from fission reactions.
As you can see, this is a fission reaction, nuclear fission. So it's decay basically, yeah. And as you can see, that's the design of nuclear reactor, and it is quite likely that some of you will work in Indonesian nuclear industry because there is a lot of demand, not only in Indonesia but in many other countries, for nuclear energy and for nuclear weapons. And usually they hire many computer professionals to help with development and with safety. So maybe you will work for this industry in Indonesia. Though I hope that you will work in the West, somewhere in North America or Western Europe or Australia, New Zealand, Japan, Korea, in some of those places. That's my hope, because there are more opportunities there and it is safer. You can breathe clean air, it's clean, high living standards, good quality of healthcare, etc. Yeah, so of course it's hard in the West as well, but maybe you can consider working in the West. That's my hope. Okay. So now let us please discuss nuclear fusion. Nuclear fusion. So that's basically, I want to find. Oh, that's the one.
1, 0. This is the record-breaking reaction. It is more than 150 million degrees centigrade. 10 times hotter than the heart of the sun. And it happened here, the world's most powerful fusion plant, Jet Fusion, in Culham in Oxfordshire. It is, say the team here, a landmark for this technology.
These results are really significant because what we've managed to demonstrate inside Jet is that we can create a mini sun, the right kind of mini sun, hold it there for a sustained period and get really good performance levels, which is a major step forward in terms of our quest to get to fusion power plants.
Most nuclear reactors use fission. That's when big, unstable atoms like uranium are split in two, releasing lots of energy and radiation. Fusion is different. It involves forcing atoms of hydrogen together, fusing them to create helium, as well as lots of energy and just a tiny bit of short-lived radiation. Creating mini-stars inside reactors like this is one of the greatest technological challenges humanity has ever faced. Get it right and holds out the potential for producing almost unlimited supplies of energy pretty much forever. The key part of this reaction only lasts for 5 seconds and only generated enough power for 60 kettles, but it is an important proof of the principles of fusion. But it means there is still lots of work to do. Do you think you'll see commercial fusion in your lifetime?
Yes, I do think we will see commercial fusion.
You're confident we will.
I am confident. I want to believe in it.
So answer me this, why is it taking so long?
It is hard. It is really hard. It is very complex, but it's worth it, and we just have to do it for the future.
Fusion energy is carbon-free, but it is not going to be ready in time to get us out of the climate crisis. That shouldn't stop this research, say supporters. The enormous promise fusion holds means we've got to keep working on it. Justin Rolat, BBC News, Oxfordshire.
Okay. So as you can see, still a lot of work for controlled nuclear fusion. But it's worth it. It's worth it. So if you understand this or whatever you understand, please write for question 31. Yeah. So now I would like us to look at antimatter. There we go. Antimatter. On this short video.
Pretty much everything in the universe is made out of matter. The Earth, air, you and me, stars, interstellar dust, all matter. By which we mean that these things are made out of electrons and quarks, and very occasionally other rarer matter particles like muons, tauons, and neutrinos. All of these particles are, at their fundamental level, excitations in everywhere permeating quantum fields. But as the famous quote goes, for every particle, there is an equal and opposite antiparticle, an opposite excitation in the everywhere permeating quantum field that has all of the exact same properties as that particle, except opposite charge. And since these antiparticles are opposite excitations of the quantum field, when a particle and antiparticle meet, they annihilate and destroy each other, which is pretty much exactly like how the equation x squared equals 4 has two solutions, 2 and minus 2, with the same value but opposite sign. And when they meet, they annihilate. Every fundamental particle has an antiparticle. There are antiquarks, antineutrinos, antimuons, antitauons, and of course anti-electrons, though we call them positrons. Since antimatter particles are essentially identical to regular matter, other than the opposite charge thing, they can combine together in essentially identical ways to form antiprotons, anti-atoms, anti-molecules, and in principle, anything from anti-ants to anti-Matterhorns. We can also make the really cool positronium atom. It's like hydrogen, except instead of an electron orbiting a proton, it's an electron orbiting a positron, until they annihilate each other in under a nanosecond. Because every particle of antimatter annihilates with regular matter upon meeting, it's really hard to make anything big out of antimatter. At this point, we're still only able to make and contain a few hundred antihydrogen atoms at one time. And when a particle and antiparticle annihilate, the energy has to go somewhere, which is why matter-antimatter annihilations have been proposed as bombs. But naturally occurring antimatter is hard to come by. So unlike a uranium fission bomb, which allows us to release the bottled energy of the supernovas that forged the uranium in the first place, you'd have to put all the energy into an antimatter bomb yourself by making antimatter, which you do by agitating empty space into pairs of matter and antimatter excitations. Kind of like hitting 0 with a hammer to get out 2 and minus 2, except instead of a hammer, you use a particle accelerator or high-energy photons of light. Photons, incidentally, have 0 charge and so are their own antiparticles, in the same way that 0 is equal to -0. In fact, mathematics has always been closely tied to antimatter. The mathematics of relativistic quantum mechanics predicted the existence of antimatter for years before any had ever been discovered. The fact that there's so little antimatter around in the universe to discover is both an obvious thing, because if it were around it would have destroyed us, a good thing, because it can't destroy us, and a puzzling thing. If matter and antimatter are basically identical mirror images of one another, why did the Big Bang produce so much more matter than antimatter? No one knows, but to physicists, the answer matters.
Hey, this is Henry. Thanks for watching this video. It was brought to
Okay, so if you understand antimatter, please write about it in question 31. So, theory of everything. So,
Suppose you're ambitious enough to try to describe everything in the observable universe in one single mathematical equation. Done. Okay, so that doesn't include gravity or a few other little things, but the point is, this equation describes with incredible precision what the Earth is made of, what keeps the sun burning, what allows us to breathe, taste, mow the lawn, blow things up, and watch internet videos. All in one equation. And it's humbly called the Standard Model, because even when they discover the most accurate scientific theory known to man, physicists are modest. Now, the universe is a pretty big place, maybe even infinitely big, so it's reasonable to think that you might need a lot more than just one equation to describe it all. So why is the Standard Model so simple? For starters, it's more like a recipe. And just as a recipe for cake assumes you already know how to sift flour, beat egg whites, build an oven, and grow wheat, this equation assumes you already know about path integrals, gauge theories, and so on. So there's a lot more than meets the eye. And why do an incredibly small set of mathematical rules appear to govern the universe? Well, that's a deep and unanswered question. But the data show that math is the language of the cosmos. Pick a few elementary particles, set them on a high-energy collision course, and bam! When the sparks fly, the Standard Model will describe the fireworks, to 12 decimal places of precision. Anyway, in the next few minute physics videos, we'll explain all sorts of the cool ingredients that make up the Standard Model, like quantum fields, fundamental forces, quarks, gluons, ghost particles, and of course, the Higgs field. It's an ambitious task, and I hope you're ready for it.
okay, so theory of everything is something which we need in physics. Yeah. Okay, I think we're about to have a break because each Google Meet meeting is for 1 hour, so I will try to make another meeting in a couple of minutes. Maybe you ask questions or give comments while we still have a couple of minutes left. Okay. So if you don't ask questions and if you don't give comments, then maybe we can start watching another video. Let me see. General relativity. No, this one. I want a short one. This one.
Albert Einstein's theory of general relativity completely changed the notion of the universe. It shed light on the birth of the universe, planetary orbits, and black holes. It also has very practical uses, like in GPS navigation. What exactly is this theory, and why was it so revolutionary? Until the early 20th century, physics was mostly explained in terms of Isaac Newton's laws. For Newton, gravity was a force generated by the mass of an object, causing them to attract to each other, heavier objects pulling others more intensely. This is why we stand on the ground on Earth, said Newton. It attracts us to its center, and it's why planets move around the sun. But imagine if the sun disappeared completely. According to Newton's theory, the planets of the solar system would instantly abandon their orbits, as there would be no gravity attracting them to the sun. For Newton, gravity is a force with immediate action, regardless of the distance between the bodies. But according to Einstein's calculations, light was the fastest thing in the universe. Nothing could travel faster than light, not even gravity. Light takes about 8 minutes to cover the nearly 150 million kilometers that separate the sun from the Earth. So, if the sun disappeared, how could the Earth go off its orbit before us Earthlings stopped seeing sunlight? Problems like that suggested to Einstein that gravity could have a different explanation than Newton thought.
Okay, so we're about to have a break for maybe a couple of minutes. I will start new meetings soon, so enjoy your break for a couple of minutes, okay? Enjoy your break. So let's see if we can continue watching this. Welcome back, welcome back.
Between 1905 and 1915, Einstein developed the theory of general relativity. He imagined the three dimensions of space and the dimension of time together as a kind of fabric surrounding us, shaped by the presence of celestial bodies. He called it space-time. Imagine the sun as a heavy bowling ball placed in the middle of a trampoline. The ball makes the surface of the trampoline dip, right? This curvature is what we feel as gravity. So for Einstein, the Earth and the other planets remain in orbit not because the sun attracts them, but because the sun is such a massive star that other celestial bodies follow the curve it generates in the space-time fabric. Now, gravity is no longer considered a force of attraction between two bodies as Newton thought. It is an effect of the space-time curvature on bodies. So according to Einstein, what would happen if the sun disappeared? His theory says this disturbance in space-time would form a gravitational wave that would travel to the planets at exactly the speed of light. That means we would see the sun go dark at the same time as the Earth changes its orbit. In other words, what Einstein demonstrated is that until then, we had been seeing the universe in the wrong way. The general relativity theory turned Einstein into a world celebrity. Because of him, science and our imagination could fly higher and higher. General relativity not only surprises scientists, it fascinates us all.
Okay, so general relativity. Well, it's kind of a little bit of an old theory because these days the demands for gravity theory are much stronger than, let's say, 100 years ago. So we need a better theory. For example, maybe string theory can help us. String theory. Yeah, where's the guy?
Beautiful tree. Imagine I have a beautiful tree that's filled with oranges. And I ask myself, what is the orange made of? How do I answer that question? Well, I want to look deeply inside the orange, so I magnify it. And I magnify it again. And if I keep on doing it deep inside, sooner or later I begin to see molecules come into view. But molecules are not the end of the story because the molecules, I can enlarge them. And if I make them big enough deep inside, I begin to see atoms. Atoms are not the end of the story too because we have electrons zooming around the nucleus, deep inside, mostly empty space in the atom, but deep inside, we see the nucleus. So if I grab that and magnify it, I see that the nucleus is itself made of particles, neutrons and protons. And if I grab one of the neutrons and magnify it, find yet further particles, little tiny quarks inside. Now that is where the conventional ideas stop. String theory comes along and suggests that inside these particles there is something else. So if I take a little quark and I magnify it, Conventional idea says there's nothing inside, but string theory says I'll find a little tiny filament, a little filament of energy, a little string-like filament. And just like the string on a violin, I pluck it and it vibrates, creates a little musical note that I can hear. The little strings in string theory, when they vibrate, they don't produce musical notes, they produce the particles themselves. So a quark is nothing but a string vibrating in one pattern. An electron is nothing but a string vibrating in a different pattern. A neutrino, nothing but a string vibrating in a different pattern still. So if I take all of this back together, I have my ordinary orange, and if these ideas are right, they are speculative, but if they are right, deep inside the orange or any other piece of matter is nothing but a dancing, vibrating cosmic symphony of strings. That's the basic idea of string theory.
Yeah, string theory. So how about exceptionally simple theory of everything? Apparently, see, exceptionally simple theory of everything. I want to find something short. Let's go on. Maybe we can watch this one. What do you think?
Garrett Lisi's theory of everything unites gravity with the other fundamental forces of nature using this intricate pattern called E8. Elementary particles are placed on each of its 248 points. Red, orange, green, blue, and purple triangles represent various quarks, and yellow and grey triangles denote leptons, a type of particle that includes electrons and neutrinos. Particles that carry a force are depicted by circles. Rotating this model reveals how the fundamental forces are hidden within its structure. Lisi uses a star-like pattern to show the relationship between gravity and the electroweak force. The green circles depict the particles that carry gravity, while the yellow circles represent the particles that carry the electroweak force. The blue circular gluons that carry the strong force emerge from the center. Here, electrons and neutrinos fall to the center, forming another star shape. At the same time, quarks and antiquarks cluster around the edges. Within each cluster, the quarks congregate into families of 3, with each family member forming the point of a triangle. The hexagonal pattern that Lisi uses to describe the strong nuclear force is also contained in the E8 model. Using simple geometry, the pattern predicts how the gluons that carry the strong force will interact with quarks. And rotating the model again brings it right back to the beginning.
Okay. So this is one of the theories of everything. He talked about it on TED. I hope you watch TED Talks. They're quite long, so it's hard for us to watch it in class, but please try to watch it in class. Yeah? Maybe we can watch this video. This guy is quite good. This one.
Brian Cox, without hesitation, repetition, or deviation, can you please explain for us as succinctly as possible I have a timer here. The rules of quantum mechanics. Your time starts now.
Well, the most basic version I know of is Feynman's version, which essentially says particles are particles, and they hop from place to place with a particular probability. And the probability that a particle that's at some place will be at some different place later is given by a very simple rule. It uses a quantity called the action, which is to do with the mass of the particle and the time and the distance. So you basically calculate these little quantities, which are to do with something called the action, and you add them up. So if I start with an electron in one corner of the room, and I say, what's the probability at some time later it'll be somewhere else? Then at every point in the room, you can assign a probability that it will be there at a later point with one simple rule, and that's it. Now, this is called the path integral formulation of quantum mechanics. That underlies everything else. You can get the rest from there. So it's a simple rule. It says, what's the probability a particle will move from A to B? That's it.
I'll stop the timer then. Very good. Well, under a minute.
Path integral formulation of quantum mechanics. Okay, Feynman. This guy is very famous.
About physics, of course, a great deal. And there I argued with him a lot because I still had strong resistance to his way of doing things.
His way of doing things now being path integrals.
Yes, I said to him, look, you've got to get the mathematics right, and otherwise it doesn't make any sense. And you've got to have some solid foundation in mathematics. It's all right to draw in pictures.
Could I interrupt you?
Yes.
I mean, when were you introduced to path integrals and his way of thinking about quantum mechanics? And maybe you could say a few words about that.
Yes, well, he talked a great deal about path integrals, but he didn't really use them. There were two aspects to Feynman. There was the way of doing physics. There was the path integral, which gave him sort of the fundamental view of the physical world, that
propagators.
Everything, before there were propagators. The path integral doesn't have propagators.
Right.
It's simply, the path integral simply says that you sum over histories, that the world just does everything it can. There are no laws, there are no rules. You start out with the world in a certain state, and then it does everything it can move in all sorts of directions. All the particles can jiggle around as much as they want in all possible ways. And then at the end, then there's a certain probability amplitude for finding a particular state in the future. And you find the probability amplitude for that future outcome by simply adding together all the paths. That's it. That's the recipe. And that makes sense. And then, so each path contributes an amplitude, which is just got by integrating the Lagrangian over the volume. And that was his recipe. He never really used that. It was that, but that gave him the physical basis. And then out of that, he concocted these working rules, which were a sort of a crude approximation to the path integral, in which you simply gave each particle a straight line trajectory. Instead of having a real path integral, you just sort of got a schematic approximation to it by having a straight line track for each particle and then joining the tracks together with vertices where they interacted. And then you had propagators telling you how the particles got from one place to another. So in order to get the probability amplitude, then you just added up the propagators. And that was sort of a crude version of a path integral. It wasn't the same thing.
Yeah, so he talks about the wave function and probability of a particle being in different places in space and time. Yeah. Okay. Let's see. Okay, so quantum chromodynamics, quantum electrodynamics. We watched this one already, right?
So Dave here. Let's talk about quantum electrodynamics.
He knows a lot about the science stuff. Professor Dave explains.
After spending some time with Einstein looking at the nature of space and time, we have to go back to the quantum realm and pay some attention to particles. In classical physics, we became aware of field forces like gravity and electromagnetism. These are forces whereby a gravitational or electromagnetic field imparts force onto some object, which generates an acceleration in that object, like a rock falling to the earth or the attraction and repulsion between charged particles. But as quantum theory progressed, it began to find a way to redefine these field forces and show that the idea of a field becomes obsolete if we are instead able to explain these forces as the interaction between certain kinds of particles. The first complete step in this direction came from Richard Feynman, an American physicist and all-around peculiar man. Building upon prior work by Dirac and others, Feynman and his colleagues worked under the assumption that the electromagnetic force was not actually mediated by electromagnetic fields, but rather by interactions between virtual photons. Let's recall from our discussion of the Heisenberg uncertainty principle that tiny particles of different varieties are actually able to manifest from nothing because of the uncertainty associated with time and energy. And particles that do this are called virtual particles because they do not exist with the same sense of permanence as other particles that make up ordinary matter. But if it were the case that charged particles like protons and electrons were able to manifest these virtual photons, then the attraction and repulsion between charged particles could be explained by the exchange in momentum that occurs during collisions between virtual photons and regular particles. No electromagnetic field would have to be referenced. This means that classical electrodynamics can be explained by quanta, and therefore quantum mechanical principles. And since light is a subject of special relativity, this makes QED a successful merging between special relativity and quantum theory. To illustrate the exchange of virtual particles, Feynman developed a system for representing quantum phenomena called Feynman diagrams. In these surprisingly simplistic representations, a straight line signifies an electron, which we know has both mass and charge. A wavy line signifies a photon, which has neither mass nor charge. And when there is a junction between a straight line and a wavy line, this means that the electron has either absorbed or emitted a virtual photon. These diagrams are mere reductions of reality. They do not contain all the information that could be pertinent to a system of one or more electrons, but they illustrate in a basic way that two electrons could approach one another and then have their paths deflected due to the exchange of one or more virtual photons that carry some momentum. Given that this is quantum mechanics, there is a ton of math we are glossing over, but the main takeaway is that the electromagnetic force has been demonstrated to be the result of particle exchange, or quanta, rather than an electromagnetic field. Quantum field theories, such as QED, seek to explain all four fundamental forces in this regard, and they have been largely successful. So let's move forward and see which force was to be updated next. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to
So if you understand quantum electrodynamics, then write about it in question number 31. Yeah. What about quantum chromodynamics?
Professor Dave again. Let's discuss quantum chromodynamics.
He knows a lot about the science stuff. Professor Dave explains.
We saw how quantum electrodynamics takes the electromagnetic force and explains it in terms of quanta, an exchange of particles that mediates the force, virtual photons in this case. There are three more fundamental forces to go: the strong and weak nuclear forces, as well as gravity. And for a coherent view of the universe, we must be able to explain each of these forces with its own quantum field theory. For the nuclear forces, this will require that we familiarize ourselves with a brand new type of particle, the quark. In general chemistry, we learned how J.J. Thomson's cathode ray experiment brought about the realization that atoms were not the smallest things. And we soon realized that atoms are made of protons, neutrons, and electrons. But as it turns out, protons and neutrons are in turn made up of smaller particles still. And these are quarks of different varieties. The name quark comes from the writings of James Joyce, who spoke of 3 quarks for muster mark. As quarks typically come in groups of 3, the title seemed apropos. These quarks also come in 3 kinds of color charge, which refers to the 3 kinds of color perceived by humans: red, green, and blue. This does not have anything to do with the actual phenomenon of color. It is just a way of categorizing quarks. And since chroma means color in Greek, quantum chromodynamics became the name of the quantum field theory that deals with quarks. Protons and neutrons are each comprised of 3 quarks, which are forever bound. Quarks of different color charge exert an attractive force between one another, like the electromagnetic force between particles of opposite electrical charge. But the difference is that the electromagnetic force weakens as particles of like charge are pulled further apart, whereas the attraction between quarks will strengthen as they are pulled apart. So they always stick together. Protons are made of 2 up quarks and 1 down quark, while neutrons are made of 1 up quark and 2 down quarks. Up quarks have a 2/3 positive charge, and down quarks have a 1/3 negative charge. So, doing the math, we can see how we arrive at +1 and 0 as the charges on the proton and neutron. There are other types of quarks beyond the up and down quark. There are also top, bottom, charm, and strange quarks, which have different properties. We must understand that the attractive force between quarks is what keeps the particles of the nucleus together. It is the strong nuclear force capable of keeping positively charged protons together against their electromagnetic repulsion. And just like QED did for the electromagnetic force, QCD shows that the strong nuclear force is mediated by the exchange of quanta called gluons. It is the exchange of these gluons, which come in 8 varieties, that keeps an atomic nucleus stable. We can see that our quantum field theories are getting more complicated, as QED needed just 1 particle, the photon. The quantum field theory that governs the weak nuclear force needs 3 particles in the form of W and Z bosons. But the strong nuclear force, as we said, requires 8 gluons. Okay, let's slow down for a minute. Quarks, bosons, gluons, what is going on? What happened to just plain old protons, neutrons, and electrons? As much of a headache as you may now have, we need to accept that the development of quantum theory brought along with it dozens of new particles that need to be categorized and understood. Luckily, we have a model that organizes all of them nicely. So let's learn the basics about all these particles next. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making.
Okay. So quantum chromodynamics, once again, if you understand what it is, please write the answer in question number 31. Okay. So this one is also very important.
Hey, it's Professor Dave. I want to tell you about wave-particle duality.
He knows a lot about the science stuff. Professor Dave explains.
So let's take a break from atoms and look at something else, light. For some time, we had known light to behave as an electromagnetic wave. For this reason, light is also called electromagnetic radiation. Light waves have both a wavelength, the distance from tip to tip, and a frequency, the number of waves that pass by a point per unit time. They are inversely proportional, since the shorter the wave, the more of them that can go by per second, resulting in a higher frequency. These variables are related by the following equation, in which c is the speed of light, about 300 million meters per second, the speed limit of the universe. The electromagnetic spectrum shows light of all the different wavelengths, from gamma rays to radio waves, including this tiny sliver in the middle, which is visible light, the light we can detect with our eyeballs. The wave theory of light was very useful for a time, but it could not explain the photoelectric effect. This was the observation that if a certain metal plate is irradiated with light, an electron is ejected, which can be detected when it interacts with a positively charged wire or plate sensor. The incongruity was that the ability of the light to eject an electron depends only on its frequency and not its intensity. So if the beam was below a certain frequency, even a very intense beam with a lot of light could not eject an electron, whereas above a certain frequency, the faintest beam possible could do it. This seemed strange, and a famous fellow named Albert Einstein solved the problem by extending a concept developed by Max Planck just 5 years prior. Planck proposed that energy is not continuous, but rather is quantized. That is, all energies are multiples of the smallest fundamental unit of energy, the Planck energy. In fact, quantum theory went on to show that everything is quantized, space and time too. So you can't infinitely subdivide them. You'll eventually get to a smallest thing that can't be divided further. But more on that in the physics course. Einstein extended what Planck said about energy and rationalized that light must also be made of quanta, which he called photons. These are particles of light. This explained the photoelectric effect because an electron is ejected when struck by a singular photon with sufficient energy. It only takes one photon, so even the faintest beam above a certain frequency would be able to do it. But if none of them are of that minimum energy, no matter how many photons strike the sample, an electron will not be ejected. It was found that the energy of a photon can be given by the following equation according to the frequency of the photon and Planck's constant. We now have to accept that light obeys wave-particle duality, meaning it is both a particle and a wave at the same time. Confused? You should be. This is the first discovery in a series that brought about the quantum revolution, completely changing the landscape of physics and how we view the universe. Newton's laws no longer reign supreme in the world of the very small, and the universe became much stranger almost overnight, thanks to Einstein and others that were inspired by him. Thanks for watching, guys. Subscribe to my channel for more tutorials.
Okay. Questions, comments, please. Okay, let's look at Maxwell's equations.
Professor Dave, let's learn about light.
He knows a lot about the science stuff. Professor Dave explains.
Since we've been able to look up at the sun, we've been aware of light. As darkness is one of very few things that we instinctually fear, we have always bestowed light with godlike properties. But for all of antiquity, we had no idea what light really was. Figures like Newton and Huygens worked with light in the 17th century, but a more sophisticated description of light, which we call classical electromagnetism, was developed largely by James Clerk Maxwell in the 19th century. This theory depicts light as a transverse wave composed of oscillating electric and magnetic fields, which are at right angles to each other and perpendicular to the direction that the wave moves. We will learn more about these fields later. Just like the kinds of waves we have previously discussed, electromagnetic waves have amplitudes, wavelengths, and frequencies. But instead of different frequencies producing different pitches, like sound waves, different frequencies of electromagnetic waves produce different kinds of light. If the light is visible, these frequencies will correspond to different colors. Frequencies greater than this will exist as UV radiation, X-rays, or gamma rays, and frequencies less than this qualify as infrared radiation, microwaves, or radio waves. All of these phenomena are collectively referred to as electromagnetic radiation, and they can be found on the electromagnetic spectrum. Here we can see all the wavelengths and frequencies ranging from radio waves to gamma rays, and we have found some technological use for all of these in modern society. Even though they seem dramatically different, some requiring things like antennas or other equipment to manipulate, all of them are fundamentally the same thing as the light you can see with your eyeballs. They are just of different wavelengths. All electromagnetic radiation moves at the speed of light, which is about 300 million meters per second in a vacuum, the fastest speed possible in the universe. This is fast enough to get from here to the moon in about a second. And since we know that all waves move at a speed that is equal to their wavelength times their frequency, this product will be equal to the speed of light for any type of electromagnetic radiation. How is it that electromagnetic radiation is produced? To answer this question, we have to learn about electric fields, which are coming up soon. For now, let's check comprehension.
Can you answer that? Electromagnetic waves, right? Electric and magnetic fields, well, yes. Yeah. Okay. I thought it was electromagnetic field, but it's electromagnetic radiation, which is probably more accurately and more precisely. Okay, so questions, comments, anything? Look, please do try the task too, and I will try to make final exam based on task 2 if everything is okay. And yeah, just try to watch YouTube videos, go to websites, check out the textbooks, Wikipedia, YouTube, whatever you can, yeah? So try to enjoy it, and it seems that it is likely that your future work will be connected with physics, because it seems that everywhere physics becomes more popular and more demanded, okay? So good luck with that, and if you don't have questions and if you don't have comments, can we finish for today? I hope we can finish for today. So please try to enjoy physics and try to use physics in everyday life, like for security, safety purposes, like electricity is a danger, heat, traffic, you know, cars, motorbikes, trucks, all those things, you know, can be dangerous if you don't know physics well enough, yeah? So I hope you can use physics in that sense. And also, maybe you will be working in nuclear facilities, for example. So it's quite likely, especially if you are in Indonesia, I think they will need IT professionals, information technology professionals working in the nuclear sector, okay? Anyway, good luck. Thank you so much. Terima kasih banyak. Thank you so much for your time and for your effort and for your patience, okay? Good night. Bye-bye. Okay, bye-bye.